very interesting introduction to me that I'm happy to some extent it summarized. I'm very happy about it. Uh, so I'm also very happy to be here after a decade, even though I've been here several times before. The past decade I could not come, and I hope I will continue to do for some more time later also. Thank you. Now, I'm going to do slightly provocative talk about what is called fuzzy dark matter. Another name for that is ultralight dark matter. But before I introduce the thing, there are some philosophical and other motivations which drove me to this because I'm originally a high level particle physics kind of person, and there is always discussion about something like dark matter. What is it? Can we find it experimentally? That's a question which people always ask, and I was also interested in that. I'm not satisfied with any of the results so far at that time. People started looking at string theory, some particles from there, imaginary things, etc. I was only asking whether there is something which we can already know it exists, probably we can associate. That is one of the motivations. The second motivation is, I will mention here as my third slide. So I'll start without much more ado. So this is going to be my plan, and don't worry about so many things. I will skip many of them because this was prepared for several other places, and whenever I needed to match with the interest of the local place, I added a few more slides, etc. So I will skip some of the slides from here. Okay, so this is my addition. Bernard Riemann, because this place is gravity. Now, if you're going to talk about gravity, then you have to talk about relativity. And if you have to talk about relativity, you should somehow bring in geometry also. So, who is the person who gave the idea of axioms of geometry? Of course, apart from Euclid, he gave the Euclidean geometry. Now, Riemann in 1855, he gave this habilitation talk to become a professor. In those days, people have to give a talk in front of the hall, and there will be several professors sitting there, and people like Gauss and others were sitting in the front, and people will ask questions. And the habilitation talks usually go for a few hours, maybe 3 to 4 hours. I'm not going to talk like that. It will be just 50 minutes, and I'll stop and wait for questions, but you can ask me questions even before. So he gave the axioms of geometry in this habilitation form. That itself is a big story. I will not mention here. But the interesting thing is towards the end of that talk. In fact, that talk had only one equation. That equation is what you call as FR matrix. That's what he has there. And he made this famous remark: the distance between 2 points, instead of being dxi dxj, you can make it as gij dxi dxj, and gij can be function specs from there, and that is the step which Gauss was looking for. He could do it in 2 dimensions, but how to do it in 3, 4 at least? That is the question. He didn't have an answer, and Riemann had an answer. That was the basic thing. Now, after giving those axioms, towards the end, he gave, made some, in my opinion, very profound remarks. He said, after telling that I have given the axioms, but is it true at the infinitesimal level? When the 2 points are very close, or when the points are too far away, is it true? And very interestingly, he even introduced the word, the thing, quanta of space in that talk, which is very interesting by itself. So when he introduced the distance between 2 points, which are extremely small, he brought the idea that in order to measure that distance, I need a rod. And the rod he talked about was a light rod, which means the wavelength of light. And the wavelength of light, when you use it to measure, the physics of that wavelength of light, that light, will come into the play, even in telling about geometry. This is basically the question he asked. And both at infinitesimal and infinite level, there will be problems with whatever he has given. Till then, there is no problem to the extent he was trying to give. Now, these are now linked to the ultraviolet and infrared properties of quantum field theories and including quantum gravity, if I am talking about, it plays a role there. That's basically the philosophical content of his talk towards the end. His argument was we don't know how to measure lengths of that kind of thing. Mean you need a wavelength which is almost plane. Then the physics of that at that level will also need change. But he was not too worried about, and the compactness and other issues also there. So this is basically the thing. But my suggestion to students and others is to read that particular brilliant article. It's very profound. Okay. Now I jump to Einstein. Einstein in 1915, through his general relativity, brought out the connection between gravity and geometry. And then for him, the axioms of geometry of Riemann naturally became axioms of gravity. In fact, he was taught by Grassmann. In fact, I was recently in Marcel Grassmann meeting, and I realized how important Grassmann's work were for him. Okay, 100 years have passed. Now the connection is understood. The laws of matter, which Riemann was concerned about towards the end of his thing, became clearer because we know about classical and quantum theory of matter to a reasonably good extent at very small scales, atomic or nuclear scales, which helps now to understand it better. So if we now go back to Riemann's remarks about changes needed to axioms of geometry at the infinitesimal and infinite, which means we will need changes for the gravity also, because geometry and gravity are related. Okay, so this is the basic philosophy which actually motivated me to get into this. Now my journey. My journey in this topic came from purely quantum theory. What is the thing? I essentially asked, like Naresh was posing, should his mass of sorry. His mass of photon. Am I audible? Hello? Hello? Okay. Is mass of photon zero? It shouldn't be massless. For all our practical purposes, it is massless. For all the experiments, etc., which we have done. But are we sure it is zero? That is the question. Does it have a very tiny mass? Can I distinguish it? That is the kind of question. And very interestingly, I was interested in this because in quantum field theory, when I do QED, there is some infrared problem. Whenever I do calculations, the photon is going around in a loop, I do an integral over d4k by k square. This is basically the thing. And when k square is zero, massless, there is a divergence. So we have to worry about what is called the infrared problem. That's what forced me to look into that particular question. If it is tiny mass, it is a small mass, then there is no problem. It is not divergent. Then, so I asked that question, and people have solved this problem in particle physics 40, 50 years back with some kind of a construction which are artificial, and several things have been done at that level. Now, when I asked this question to solve this problem, I gave a talk in Dublin Institute of Advanced Studies, and where Schrodinger was there about 100 years back, and he actually gave a same talk. And the title of the talk was Mass of Photon Mass is Zero, and he even published. Boss was his postdoc at that time. And the question was very simple. If photon has a mass, it will have 3 degrees of freedom. If photon is massless, it is 2 degrees of freedom, 2 polarization. Left hand, right hand polarization. That's all is there. So if you have mass, then the 3rd degree of freedom which comes out. How will it affect? But it will affect the following: simply black body radiation. You do the calculation, you take in a black body the radiation, and then you compute. Conventionally, you come standing modes which are there, you compute find out what is the relation between frequency and this thing, and then you integrate the total density of energy density, and you get to how much radiation will come out. This is the basis of all the luminosity and other calculations that you do at a particular temperature, and the answer is sigma T power 4. And that is obtained by this density which is there. There is this factor 2. The 2 is there because you compute on 1 degree of freedom, multiply by 2. And this 3 degrees of freedom, should I multiply by 3? If I have 3, then the calculation will lead to a sigma T power 4, where the value of sigma will be 4. Obviously, that is experimentally measured. Should I do that? That is the question he asked.
Excuse me. But even if photon have a very tiny mass, then photon scattering should be possible, and that's experimentally nowhere observed.
No, it does. Photon, they themselves don't interact.
So that's my point. That's why if they have a mass, they should interact.
Why should they interact?
A mass should scatter.
With gravity, through gravitation. Where is the gravity? There is no charge for that. Through gravity, yes, I'll come to that. But there is no mass. If it is gluon, I can understand. The gluons do interact. Non-abelian theory massless particles do interact. But photons don't interact on this. It's a free particle. That's all. Okay, I'll come to that. So this is the famous question: Bose versus Einstein, 2 or 3, should be multiplied by 3. And the answer Schrodinger himself has given in his paper: no, we should not multiply by 3, even if it is massive, if the mass is very, very tiny, extremely tiny. That is the answer. Why is it so? The answer is simple. As long as you couple that vector potential mu to a current J mu, the current is concerned, dv J mu is 0. So what is the interaction? You write A mu J mu. The longitudinal photon, other than the transverse photon, will have a typically of the form d mu phi. So you have d mu additional term as d mu phi J mu, which you integrate by parts. You will have 5 times dv J mu, which is 0. So it's only surface term which will be. If the mass is tiny, you can assume that the surface is too far away. So there is no additional contribution. And so this is what he wrote in his paper. Even if we find in nature, the limiting case is realized experimentally, we find it to be 0, they should still feel the urge to adumbrate a theory which agrees with experience in approaching to that limit. Even if it is 0, we should be able to approach to that. That's what he said. Okay, so this is basically the idea. So, why did I write Bose versus Einstein? Bose wrote this paper in 1924, I mentioned that, where he, after writing the black body radiation formula which was there, he called it spin of photon. Okay, he called it spin of the photon, but it has 2 degrees of freedom. Somehow surprisingly, it is at 2 degrees of freedom. Einstein took his pen, when he corrected it, he removed the word spin of the photon, he called it polarization of the photon. Because polarization is to us assume coming from Maxwell's theory, which is the polarization of the photon. So he somehow preferred it. So it was a conflict thing which was made by Einstein, change it to polarization, which was essentially he didn't want to call it spin of the photon. This is basically the idea. So this is basically the thing, but actually you will find Bose was right and Einstein was wrong. Photons have a spin which has value 1. The helicity is 2 because it was a thing, and that helicity is what we call the 2 degrees of freedom. Okay. And the photon spin was measured by Raman and others in India. Okay. So what did he do after that? I will not explain this in detail. He said, okay, if there is a mass, let me put the mass and find what is the limit for the mass, experimental limit for the mass. So this is a simple calculation. This is that equation number 1, which is only a straightforward equation. If m gamma is 0, that is 0. Left hand side is del square A. And then solve this equation and you find a new result. What is the result? You consider the Earth as a magnet, and the magnetic field due to the Earth's magnet is there. You find the magnetic field at every point. Find out if it is massive photon to have a value. If it is massless photon to have a value. The difference between them can be experimentally measured. And that's what he did. And that calculation is simple, and that led to this kind of a formula, the Bx is extra contribution which is there. And the answer is simple. He gave the answer that the mass of photon should be less than 10 to the power minus 47 grams. Should be less than 10 to the power minus 47 grams. People have improved the data using the same geomagnetic fields and got it as less than 10 to the power minus 48. This limit the geomagnetic fields. The magnetic fields on the surface of the Earth. That's all, as simple as that. Okay. Now you can use cosmology to the galactic magnetic field, and there are doubts about it. And the answer which it gives is it should be less than 10 to the power minus 56 grams. But this is taken with pinch of salt. The result which is there in particle data book, even now, is only this 10 to the power minus 40. As of now, the results. Okay. So,
other way of will it not conflict with the your flux conservation?
There is no problem with current is concerned.
When the current is
So the one thing is that longitudinal photon interacts with matter. See, your transverse photons interact with matter, longitudinal photons interact with matter. That interaction with matter for the longitudinal photon is very, very tiny because it is due to derivative coupling. It's only the long wavelengths, mu phi.
if I take photon as the carrier for the electromagnetic interaction, now I want the Gauss law to satisfy.
That will be only that to Gauss law is for electric field.
Yeah,
Electric field will be still coming from only transverse component. It will not be affected by it. Transverse component is the only thing which will be affected. The longitudinal photon will not affect. Okay, I can give the same mass in terms of electron volt, which you are familiar with. It is less than 10 to the power minus 16 electron volt, and 10 to the power minus 18 is what the particle data book gives now. Okay. Now you can ask the question, if photon has mass, different frequencies will have different velocities. So there are several experiments which have been done. From there, whether we can infer something, the answer from that is this thing, the delta C by C is less than 10 to the power minus 5. So it is actually something where we are not able to conclude better than what you have already given. That's what is the answer for that. Okay. So now comes to the field theory part. Now if I add mass to the Maxwell's equation, Maxwell's action, by the term m square mu, people m square mu, people break gauge invariance. So gauge invariance is lost. So there are two problems. Gauge invariance is lost. When m goes to 0, there is a discontinuity in the degrees of freedom from 3 to 2. These two problems were there, and it was bothering people at that time. And there is a brilliant person called Stuckelberg. He solved both of them at one shot. And what he did was the following. So what he did was this thing, that Lagrangian is m square mu square. He added 1 by m d mu phi. He added an extra field phi, and the gauge transformation of mu is cancelled by the gauge transformation of this phi. And that is what I have written as equation 5. And this equation which I have is completely gauge invariant. It's completely gauge invariant, and it passes 3 degrees of freedom even in the limit m goes to 0, but the 3 degrees of freedom decoupled as 2 plus 1. One scalar field is there, one transverse component is there, so there is no discontinuity. Gauge invariance is preserved, etc. But what he has given in 1940s, Stuckelberg, outstanding scientist, he has given Higgs mechanism. This is nothing but Higgs mechanism. I'll tell you how it is done. So Higgs mechanism is the following. He introduces a scalar field complex skeleton, couple it to the electromagnetic field, and make this thing as a Higgs field R and e to the power I5, the phase. Okay. You make R to be extremely massive, very, very large mass, so that it doesn't play any role except for a number. Then what you get is whatever Lagrange feature. So, in the limit of mass of R is very large, you get from Higgs mechanism Stuckelberg model. That's what is there. Okay, now there are other methods of giving mass which I have pointed out here, but as I told you that I'm going to skip several pages, and this is one of them because it is irrelevant for my. So what now? The thing is, Stuckelberg field, which is extra 5 field, which is there, does not interact with matter in a length scale. The length scale is 1 over m because 1 over m dignified is coming. In a length scale of 1 over m, actually I should call the length scale as h bar by nc. That is what I'm just taking h bar as 1, c is 1. That 1 over m length scale, there is no interaction between them. So it completely in that thing, one scalar field is there, 2 degrees of freedom are there, completely fine. So what can I do with that? And that's what Schrodinger wanted, and that is there. But it has energy, as he pointed out. And if it has energy, it gravitates. If it has gravitating, can it play a role for dark matter? So this is basically the question. What the hell is dark matter? I'm going to mention one slide for the benefit, which I usually keep that for master students in other places. I will mention that. But we are calling light as dark. That's the most important. Okay, what is dark matter? Now, basically, this is what is Kepler's law will tell you that the planets far away will have a velocity which is small, much small, and that is what the term A will give. Whereas what you experimentally find from any galaxy is, for a large distance, very large distance, this is almost a constant B. This is what you find, and this was discovered much earlier, and people associated that there is a matter which does not interact with light, does not produce light, and it is there and gravitates, and it is able to do this kind of thing. Okay, so this is basically explaining what is dark matter to. I will skip this because all these things are probably many of the students also here because how the dark matter was discovered and there is issues which go with that because that will save some time. In particle physics, we immediately look for if there is a dark matter which does not interact with light, with any other known things, I should be able to tell what it is. So immediately people look for, so in supersymmetry there are several particles, in string theory there are several particles, in QCD there is an axion which is done, and several things, and there is objects of this kind are there, and some people who are not satisfied with any of this thing, they will say that the theory itself, gravity theory should be modified. Essentially means if acceleration is very, very tiny, then gravity as proposed by Einstein is incorrect, so we have to modify. This is what is done. Okay. So this is a thing, but I will come to the crucial point here. Fuzzy dark matter is a model. It suggests that dark matter is composed of ultralight particles. The particles whose mass is tiny and who having constant wavelengths at cosmological scales, constant wavelength should be cosmological scales, with mass of this order, 10 power minus 20. Is there a particle which we know? The only particle as far as I know is the photon which I mentioned. All other particles which are there, new particle which nobody has found out, but we know about photon. So this is basically the idea. Okay. The Stuckelberg field fits into this framework and probably can help. That is basically right. But it's not so easy. What is it? If the mass of the candidate is too small during Big Bang, etc., it will simply fly away because it travels with the velocity of so-called light, very, very high value. So there's nothing to hold it. That's what will happen, and it decouple very early. This is basically the idea. That is where again boson and string has. This is basically the thing. Mr. Bose has been coming earlier. Now he is coming in a new avatar in this framework. So again, 1924, when he proposed this whole idea of quantum nature of black body radiation, quantum nature of photons, this brilliant paper which was not accepted by philosophical medicine in England, and he sought the help of Einstein to get it published, and that's how the whole story went ahead. But one thing is, after doing that, there was another paper by Einstein with Bose's name also, if I'm right, which says that it's a new form of matter possible because the bosons will try to condense. The lowest energy, they will all condense to, will form a new state of matter, and that state of matter is called Bose-Einstein condensate. So this is basically the idea. So which was fantastic. Einstein proposed this Bose condensate could be there. Now, after proposing this thing, can you find out experiment? Now, experimentally, there is a critical temperature below which you can find the Bose-Einstein condensate. The critical temperature is given by this formula, which is there, 6. Okay? That formula says if you take, in fact, experimentally in the next page, BEC was obtained for rubidium-87 gas. Rubidium gas, they found the Bose-Einstein condensate. That is the value. So why? The thing is, it is 86 AMU, atomic mass unit, very, very high. You do your ideal Bose gas, that's all. The only thing you want to do in addition is there is a Bose-Einstein statistics. What was done by Einstein is, you do ideal Bose gas, but introduce the Bose-Einstein statistics in that, and from there you get the new state of matter, and that is what is this thing. So the critical temperature for such a mass, if you work it out, will turn out to be nanokelvin. So it is very difficult to find out. It is 10 to the power minus 9 degrees Kelvin. It is extreme.
What is the TC? How is TC obtained?
Here, this is the formula.
Formula is right.
So you do, like as I told you, you first assume that the ideal gas of particles with tiny mass, it's like marbles which are there regularly we do. Apply the Bose-Einstein statistics. Now you have the quantum theory. The Bose-Einstein tells you that a state can be there where all of them will be at the ground state. If it is 0 degrees Kelvin, all of them will be there, and then slowly they will get excited by when you increase the temperature. And you find that there is a, if the density is constant, then up to some value, it will remain in this thing. So there is a 2 sets of particles. One is at the ground state, another with slightly small number of particles which are going up. So that is your Bose-Einstein condensate.
Equilibrium.
This is the equilibrium, statistical mechanics equilibrium, which is obtained with this. That's what Einstein proved. The new thing is coming from there, and that critical temperature, if it is less than that, that situation will be there. Beyond that, it will be your regular ideal process. Beyond that, okay. Now, the value for that is nanokelvin. So you can't find. It took a lot of time. Only in late 90s that Bose-Einstein condensate was discovered because we were trying to do with this. Now, our photon, the longitudinal composite particles have a mass 10 to the power minus, let us say 20 or 22 electron volt. So, what is the critical temperature? If you work it out, the critical temperature comes out to be Big Bang temperature. It is 10 power 19, 18 degrees Kelvin. Depends on that. Okay? There are some more parameters you put. So, if a condensate is formed at that time, close to the Big Bang, it will remain a condensate for all the time because the temperature only has been going down. Okay, so this is basically the idea that any ultralight particle, if it is there, they can do this kind of magic. So this is basically the idea. Okay, I have given the evolution for the various content in the radiation era, matter era, dark energy, etc. And if I know the dark matter density now, I can evolve back, find out what should have been the dark matter at the beginning of the time. That's what I have done. Okay. So this is basically some kind of computation one has to do to get some idea about it. And the critical temperature depends on what is the mass you are going to fix. The mass is this, you have different temperatures, etc. So this is the critical temperature. Post-extreme condensate can help you. Okay. So what do you do after that? Then you have the condensate and use it to do the FRW metric and find out in galaxies how the thing can help in holding the galaxy together. Okay, this is basically the thing. And this is an equation which you have. But the point is, even though the particles are tiny mass, they travel with the velocity of light, but the condensate as a whole, very large condensate, it's a huge object. The huge object as a solitary object, it moves together and makes it very, very high mass. Okay, that is basically it. But unfortunately, you can't call it one particle because it is made up of very large number of tiny particles. So it has a structure of fluid. You should call it fluid. The Bose-Einstein condensate is like kind of superfluid. And that is what, yes.
So if one were to put a notion of size for this condensate, so basically the whole universe is a condensate.
Not the whole universe. It depends on the mass which I'm going to, and I will talk about precisely that point. I'm going to do what is the size. I'm making some estimate, what you can call the back of the estimations. I'll do that. Size of the condensate. You're right. So this is the thing. This equation was used for such particles like 10 power minus 22 electron volts by a well-known phenomenologist called Edward Witten in a paper. And well, I will try to talk about. This is the paper which he had written. And basically the idea is the following. Now when you have galaxies, there are galaxies of all varieties. There is huge galaxies like our Milky Way or even bigger. And there are dwarf galaxies, small galaxies, 1,000 stars, 10,000 stars, 1 lakh stars, kind of this thing. Now, they are all smaller in size. Okay, they are all smaller in size. So, the basic idea is whatever other candidates were there, if they tried to find a profile for the dark matter for dwarf galaxies, they all blow up at the core, which is known as the core problem. Okay, core cusp problem, which is what is the thing. But if it is a fluid, it is not like a particle, like the way various particles were considered. If it is like a fluid, that problem can be solved. That is basically the thing. So this is the thing, dark matter halos, which are playing a role in this, will help. We are interested in finding out with some kind of a simulation people have done with ultralight particles. They are not taking photons, but they are taking ultralight particles. They are getting various radius, half radius, and what is the energy and core, etc. So these are the formulas which are there, and I will not explain this formula, except there is a half radius formula which you can try to pick various dwarf galaxies, and what is the core density can also be used to hit them. So these are all ongoing work. So basically, dark galaxies have the density profile without cusp problem. With the simulation, this is only simulation. We don't have an analytic way of doing that. In fact, unfortunately today, Azim Paramspe is not here. I did have a discussion with him. He was aware of many of these issues. Okay, so this is basically the thing. Some back of the envelope calculation. What is the size of the galaxy? Size of the condensate. Typically, you expect the condensate to be the size of the quantum wavelength of the mass which you are using. Okay, that's what is going to be the. Now, you can ask the question, what is the quantum wavelength for 10 power minus 20, 10 power minus 21 electron volt, various numbers which you can put there. You can calculate that. This back, any student here will do h bar by mc, h by mc, you do that, you find out. If you do that for 10 power minus 18 or 16 electron volt, it will be 0.001 by 18. Now, when you do that for 10 power minus 22 or 10 power minus 24, it will become something like 1000 light years. So the condensate size which you wanted to have can be anywhere between them. So you can try to find out which is a good one by doing a numerical fitting or simulation work which you want to have. So then I asked a question, what is the smallest size of the galaxy? Dwarf galaxies you have. Okay, is there, if you can't have a galaxy whose size is less than the Compton wavelength itself. Okay, whose size is less than the Compton wavelength.
So this Compton wavelength itself will be redshift dependent.
That's true. I should, but as you measure, but I want to tell you that what is the size you can expect. When you measure, you'll find. Okay, that's basically the idea. So I take the Compton wavelength and 10 power minus 22 electron volts. If I try to do, the Compton wavelength turns out to be something like 100, 10 light years. 10 power minus 24 turns out to be 1000 light years. 10 power minus 23 is 100 light years. Okay. Now you can ask the question from the data which is available. In Milky Way, there are about 40 dwarf galaxies which people have seen, and simulation tells you there are about 100 to 200 dwarf galaxies there, and people call that as missing galaxy problem. Missing. They're missing because there are galaxies, dwarf galaxies must be there, but we are not seeing them because they emit too little light for us. So they are all dark matter dominant galaxies. Dwarf galaxies are dark matter. If dark matter is something like 95% in typical galaxies, it will be 98% or 99% in those galaxies. So that's what will happen, and you have the expectation from there, and the known value for the smallest galaxy is what is called SEG2. If I have written it here, probably it will come in one more slide. SEG2, which has radius or size typically of order of 120 light years. So I expect that 100 light years is my back of the envelope estimation should be the Compton wavelength, and it should be 10 power minus 23 multiplied by some numbers. So those are all experimentally you try to fit in by observation what is the best value you can give for that. This is basically the idea.
So I had a question. So suppose you have a normal galaxy, which is the galaxy location card. If the Compton wavelength, I understand that is the size of the condensate. So if it ends at a certain point, you should see after that length.
No.
There will be a fall, right?
So for a large galaxy like Milky Way, there could be many such condensates, solitons, many of them. They should form a profile which gives you that. So it is like a large collection of such things for Milky Way. But if I take dwarf galaxies, they will have only one or two, few of them. That's what I'm saying.
Yeah, but like if we look at the center of the galaxy, our galaxy, for example, on let's say nearby Andromeda, there will be one core there, right? And even if there are clumps of these condensates, there should be some discontinuity.
So that will be reflected in the profile which you are trying to work out for the dark matter profile, which should be of that thing. That requires little detailed simulation and work. So I don't have a complete control on this.
So even in this picture of ultralight matter with a very large free streaming length, let's say, compared to the usual very high cold dark matter particle,
yes,
you would still think that the structure formation has gone in like usual hierarchy of smaller structures, and then
I'll come when it started. Okay, that's the point. Next time.
Back of the calculation, relative
I should do with de Broglie wavelength to be precise, but for all practical purposes.
It also means that to match the different scales to the problem, you should have a distribution of energy.
Yeah, sure.
So
no, but the Broglie wavelength at the very early universe perhaps is the size of the universe at the time of it.
Precisely, that's what I'm going to come.
Then the condensate has formed and frozen, so your basically scale factor.
No, there will be. See, initially a lot of these things, typically at something like 10 power minus 12 seconds, when the photons, longitudinal photon also they don't form a condensate because the size is too small. Now, when the size becomes, you can ask the question, when does it become, say, 100 light years? This is the expectation. It takes about 10,000 years in the FRW calculations. So that is when some of these things will be formed.
So that's when you will form the first structure, which is basically like the size of the universe, almost.
So at that time,
At that
so, and there will more such structures will come because that is good enough for one thing. But as you evolve much more, okay, then there will be dispersal of these things and other particles, pairs which are created.
Exactly.
Yeah.
So I thought the first structure that formed was almost like the size of the universe, which goes somewhat.
It is almost the first few structures. It evolves by scales of various things which are there. Now you can ask the question. In fact, it is related to the sea. There are galaxies which JWST tells me that formed around 300 million years or 400 million years. That is the claim which is there. You can ask the question, where does it come? Okay? And that is the kind of thing which we will not have an answer unless this kind of a version of various such condensates are formed, and then they are able to put together some structure formation, which I have not yet done. This is a whole program which I have, which may help.
As you rightly said, it will form a condensate very early on. Further, it will remain condensate only because the energies are lower.
Yeah.
So any other things which are forming will be a lower energy.
Yeah.
So that is where this the idea of, if you want to, even without going JWST, one of the questions you asked is that what kind of probability distribution you have for sizes today.
Yes.
That will tell you like what kind of breakup you have in the condensate.
Right? Yeah. In fact, I don't have an idea to be precise. But these are all issues which one has to do a combination of numerical simulation and analytic ones.
Philosophically, this is very closer to forming a bigger structure and cascading to smaller structure.
Yeah.
Instead of forming a smaller structure and merging to a bigger.
Right. Yeah.
This is one. Yeah, that's yeah.
So in principle, if you have a structure, big structure like initially, there is nothing which prevents that they merge and do something also within this framework. Also, that can happen.
Gravity can.
Yeah, gravity will do all sorts of. Yeah. So that will be there always. Okay, that is there. But at the moment, this is the outline of the program which I can tell. Okay. So now I will the prediction. There are about, so this is what I mentioned. The smallest galaxy seen so far is said 2 with half radius of about 115 light years. Our expectations predict something like 100 light years. This is what I'm trying to have a hand waving argument at the moment. Okay. Now there is another one because I'm using photons, right? Whatever I said before can be any ultralight particle. But when I have photons, there's a calculation by Ryuto, even in cosmological things, which is there that if you take Maxwell-Procoy electrodynamics with finite mass is very tiny, under certain conditions develop a negative pressure. This negative pressure indicates a gravitational pull and can become dominant. So this is one of the things which also says, where is the pressure coming from? It is coming from the longitude. That is the additional one. But the length scale, which is expecting is the length scale of the Compton wavelength. The wavelength of this thing, when it is Compton wavelength, which is there, that is what the paper is quoting. So this is what the paper by Ryuto, which I can probably look for a better argument to use it. Okay. Then there is one more thing which is also called pulsar timing array, which is essentially saying that radio telescope looking for nanohertz gravitational waves. Recently, some confidence level 98%, the hum or universe, something similar to CMB, as an interesting connection to FDM, the fuzzy dark matter. The gravitational waves of the galaxy mergers of the earlier things in the early universe or some other way, if it is to affect our Milky Way pulsars which are there, and dark matter is in between in the thing, what you see in one pulsar and what you see in another pulsar, the differences which you find, if it is there, then it should tell me something about the Compton wavelength of the dark matter particle. So the average distance between pulsars will give an indication of the counter wavelength of the dark matter FDM candidate, whatever is the candidate. It may be photon, it may be something else. And such a thing was done by these people, and they expected from the data which is available, it should be greater than. Now look at, I've been telling that the mass should be less than 10 power minus 18. Now this one will tell me it should be greater than 10 power minus 24 electron. So this is the kind of a window which is available to play for our. So this is basically the thing. The same arguments can be used for ultralight axions of fuzzy dark matter. But the basic problem is all other ultralight particles which are being proposed, they have to find it experimentally. But now it is connected with the electromagnetism itself, and we can ask the question, can I find longitudinal photon experimentally? The answer is very, very difficult, but there are proposals which I can do. And one such is, again from particle physics, a spin 1 particle, massive spin 1 particle like Z boson, cannot decay to 2 photons, massless photons. This is one of the theorems which was created by Landau and Nahm in 1950. That is simple, straight, no action, no Lagrangian, nothing. Poincare invariance with Bose symmetry will give you. Now, if it is not massive photon, massless photon, but massive photon, it can decay. So one of the photon can be a longitudinal photon, one can be a transverse photon, but you are not going to discover the longitudinal photon, but that will appear as a missing energy for the problem. So this is one of the, like neutrinos were proposed for missing energy and missing momentum. This is one of the things which can be done. So, okay. So this is basically the way with several supporting things can be created. Now I have to entertain, and for that I have to change the gear. Okay, the last 5 minutes I'll give. The changing gear is this thing: Einstein's special theory of relativity and Michelson-Marley experiment. Okay, Michelson-Marley experiment established the irrelevance of ether as a medium. Right, ether medium. When you need it, you don't need it. Okay, this is what Einstein's theory told us. Unfortunately, this gentleman, Einstein, after living in 1915 general theory of relativity, he gave that irrelevance in special theory of relativity. He then went into general relativity. He asked the question, is it relevant there? That is a question. Very interestingly, there is a paper by him in 1922 called Sidelights on Relativity. And this is a mention which he has. To deny the ether is ultimately to assume that empty space has no physical qualities whatever. The fundamental facts of mechanics do not harmonize with this. This is what he says. Recapitulating, we may say that according to the general theory of relativity, there exists ether. According to the general theory of relativity, a space without ether is unthinkable. For in such space, there not only would be no propagation of light, but also no possibility of existence of standards of space and time. So this is his statement in that famous paper, Sidelights on Light. Yes.
But if you go to a local inertial frame in a given point, if suppose there was ether, then there will be a preferred frame in that local inertial frame, right? So that would violate special relativity.
So I will come to that. So the whatever matter you are going to say, whatever matter I am going to assume, has to be different. Not kind. You will say there is an ether, which is a thing, but what kind of matter it is? Okay, that's what I'm.
Michelson-Morley experiment did not tell you that ether.
He doesn't say it's irrelevant.
No. Michelson
You can manage without that.
The daily conclusion was that you cannot measure your motion relative to it.
Correct.
That's all. The
Sure.
Earth's motion you cannot.
Sure.
So
I have no dispute at all.
cannot serve as a reference point.
Sure.
But it did not deny that there cannot be this.
Precisely that remark I'll come to that. So this is See, I'm looking only for authorities to make this remark, and I'm going to have more authorities to tell me that. Okay, so this is the thing. But this ether may not be thought of as endowed with the quality characteristic of ponderable media, matter which we all know already. It requires something like Bose-Einstein condensate, which is not our regular matter, a different form of this object. Parts which may be tracked through time. The idea of motion may not be applied. This is what content of the paper is. Okay, I'm only quoting from. Okay, the next authority I'm going to show is Dirac in 1951. Okay, Dirac in Nature asked, "Is there ether?" This is the question which he asked. He answered, "We can now see that we may very well have an ether subject to quantum mechanics and conforming to relativity, provided we are willing to consider vacuum as an idealized state not attainable in practice. From experimental point of view, there does not seem to be any objection to this. We must make profound alterations to the idea of vacuum." And this is basically the way he concludes his paper in 1951. Is there ether? That is the question. And essentially, the vacuum is always having fluctuations of particle-antiparticle pairs created, and that is filling up the whole thing and making you a mess, or what we call the vacuum, etc. So that is what we call the quantum vacuum is ether. This is what his whole idea is. Okay, the next authority which I'm going to look for is John Bell, which answers your question. John Bell suggests that ether was wrongly rejected on two philosophical grounds. What is unobservable does not exist. This is the thing. But there is no specific thing. We may become observable in a different way. That is the point. And then Laughlin also quotes the word ether has extremely negative connotations in theoretical physics because of its association with opposition to relativity. Unfortunate, because stripped of these connotations, it nicely captures the way most people think about vacuum. The modern concept of the vacuum of space confirmed every day by experiment is relativistic ether. But we don't call it because that is bad. So this is what other authority which I'm quoting. So several of them I've been thinking about how do I characterize that inter space which is there. Okay, that is basically
But
there.
it's more like attaching new meaning to the ether. Ether
Yeah,
was
new
meant
meaning.
earlier.
So the new meaning is it requires quantum mechanics because Bose-Einstein condensate is needed. New ideas about Bose-Einstein statistics is needed, and also it should be so tight, like an ideal gas should have a mass which is extremely tiny. If this framework is
Yeah,
that.
so at the time when it was rejected, it had different connotation. Now
No,
it is attaching
absolutely no problem. That's, I'm not saying they were fools,
Yeah, yeah.
but I'm only saying we have to revise our thoughts.
Yeah, but there is one thing what Einstein now pointed out, that if it is not there, then I cannot have even a
Meaning of-
propagation in it.
Correct.
It is totally inert.
Yeah. Okay, let me go to another, and that happens to be my friend, my collaborator, and that's what I'm going to quote. The next point, and that is this man, E.C.G. Sudarshan. And very interestingly, E.C.G. Sudarshan, main problem with the ether in the earlier thing is if there is ether pervading everywhere, then you will say, okay, our planets are going through it, they're not affected. There is the Young's modulus, bulk modulus, what should be the velocity, what is the characteristics of that, etc. Then you want to avoid that, we just, okay, let's make ether a superfluid. Simple as that. Then your notions of that earlier notions will not apply to that. So he wrote this paper in 1976, and this is a very interesting thing I'm just pulling out. A new model for ether, a superfluid of fermion pairs, described by a macroscopic wave function pervading the entire universe, actually means galaxy, and may account for missing matter. Now remember, this is in 1974. At that time, nobody talked about dark energy. They only knew about dark matter, okay, which is from the rotation curves which are there. In order to, it was an outstanding problem in 1970s, and this is the kind of a suggestion he actually constructed a model. And this is very interesting because what you have here is the pairs charged particles, plasma particles, which are there, they form both first BCS, the thing where they form a boson out of the two fermions, and those bosons later condense. So there is a transition from BCS to BEC, which is a crossover, which is playing some kind of an interesting role, which is there in condensed matter physics in non-relativistic context, like the way earlier we had, but in relativistic people have not studied that. So that seems to be helping or useful in this framework. Some of the ideas of superfluidities, bosons in condensate, which was used in non-relativistic ideal gas, which was there, one has to revise, go back and apply it in the context of relativistic fields.
So this will serve the purpose for dark energy.
No, this is for dark matter. I don't talk about dark energy because I'm not yet said what should be dark energy. I'm only talking about dark matter within the galactic structure. I'm not talking about the whole universe. Okay, you can say this whole universe at the early time of 1 second after the Big Bang. That is the guy.
So what is the reason that we have to start with Cooper Bear kind of thing, but not just the like why
Okay, this is what I was reading the paper by Anderson just now, where it's called Anderson-Higgs mechanism. People will ask in a plasma where there are electrons are there, positrons or plasma charged particles are there, and there is radiation. Now, in that radiation becomes massive. Okay, in plasma, it has mass. If it has mass, it develops longitudinal component of the photon. Where does it come from? That comes from the electrons themselves. In fact, that is a huge discussion about this issue of origin of the longitudinal component or superbug field or the Higgs particle. Somehow, Anderson doesn't like the Higgs. He says it is fictitious. But basically, this is basically the point is that Higgs as a mode of field is there in that already. That's where this whole thing is. Okay. Okay. So this is basically. So now I go back to CMB. It's a good black body radiation, right? Extremely good black body radiation. Does it tell anything about the photons? You can fit it. So you can find that it tells me this blue, this curve is what is the black body radiation, CMB along with various estimates of error bars. Now, if I have mass of the photon is there, the formula is the following. If there is a mass for the formula, the density formula is this. It has this thing. So you just plot it. Now it will tell me you should fall within the error bars which are there, at least in this thing. So the red curve is for 10 power something like minus 12 electron volt. It should be less than that. So the CMB gives a mass of the photon should be less than something like 10 power minus 12 electron volt. But your own geomagnetic and other data gives you a better limit. To some extent, it is not contradicting with the CMB data, which is there, but we have to do something like it. Okay, so this is basically the idea. And this work was done, correct, by Julian Hick in several letters. This is the reference for that. And actually, it says it should be less than -6 electron volt, which is not a good estimate compared to other estimates. But the only thing is, he said, okay, if it has a mass, can decay, photon can decay to neutrinos. If there is one neutrino which is massless, it can decay to neutrinos, and it tries to find the decay time rate of photon so that it can find the lifetime of photon. And the answer he found is very interesting. They got the answer as 3 years. Photon will decay in 3 years. It is there in that paper. But we have looked far enough to say it is not 3 years. But how does it help? The point is, since the photons travel with the universal speed, it's very close to the velocity of the universal velocity, you have to apply time dilation. When you apply time dilation to this 3 years, it becomes 10 for 18 years. It becomes 10 for 18 years, which is much more than age of the universe. So you don't have to worry, at least according to him. But there are a lot of assumptions which he has made, which I'm not comfortable with. But it looked interesting that you can ask this question itself. Okay, so this I can extend it to what is called weak and electromagnetic interactions. I will not elaborate on this.
On creation time scale will be something similar also.
Hmm?
Neutrinos can also couple and give you photon.
Well, it depends on whether neutrinos, what is the mass of the neutrinos. Now, there are 3 neutrinos. We don't know the mass of the neutrinos. They are all going in 0.1 electron volt kind of this. But what we don't know is there are 2 relations between the 3 neutrinos, and one of them can be very, very tiny. That's what is it. We don't know that. As that is a story for neutrinos. Okay, so this I will not elaborate because the Weinberg-Salam model is one of field theory, which can be good. I took only electromagnetic, but I can do it along with Weinberg-Salam model, and that is what is done several people, and that is there in some work which was there by Ruge and IUCAA, Stuckelberg field, which is there. And these are all various things which are coming into the scene. I will try to conclude. So there are various things like whether primordial black hole can be explained from this kind of a framework, etc. on which I gave a talk in Pescara at the Marshall Grassman meeting. But the point is there are now galaxies at the 300 million years, 400 million years. If you have a galaxy of that thing, and which means dark matter must be there. For structure formation needs that. Secondly, there should be a supermassive black hole. Now, the question is, are these related? That is the kind of a thing which is interesting, which I'm trying to understand from primordial black hole itself. So I will not talk about any of the other things, but I will remind Bernard Riemann's profound remark at the infinitesimal and infinite axioms underlying the basis of geometry changes. Infinite, this is a very large distance. We know about infinitesimal in the sense of quantum field theory, ultraviolet problem. This is the infrared problem. So we should have a better idea of the notion of geometry at long scales. Okay? So to end, history of cosmology has shown that in every age, what people believe that they have at last discovered the true nature of the universe. We also believe that we are closer and closer. And these are my works which are there. And so I'll stop here. Thank you.
Open for discussion.
I want students to ask questions.
Yeah, from the other side of it.
No, everyone can ask. I'm not stopping. Everyone can. Yes.
Yeah. How does photon will have mass? Like, will it interact with the X field to attain that mass? Or will the photon interact with the X field to attain that mass? Or is there some other mechanism?
So you should introduce one way is you introduce a complex scalar field coupled to electromagnetic field which is massless. That Higgs field which you have introduced will have a vacuum expectation value, which is I wrote it as RE or I5, and that will break that symmetry, which we expect a Goldstone boson will be there, but the Goldstone boson becomes a longitudinal photon or longitudinal part of the Higgs field. So that's how the mass of the okay, it's simply straightforward calculation. It was done by Higgs, but originally the idea came from Stuckelberg.
How does this fuzzy dark matter conform to the paradigm of cold dark matter?
Well, cold dark matter can be any mass, okay, extremely small mass, but not to this range. So, all the good features of cold dark matter, this will apply. But cold dark matter has problems at the core cusp problem, which is one of the things that I mentioned, and several other issues where people will be still having a lot of discussions.
The cold dark matter particle mass, I think, constraints from your UV luminosity functions and all is about in the keV range,
Right.
1.25 keV.
Yeah, keV and
so below that is basically ruled out in some sense.
Yeah, that is
So that's why it's quite dramatically opposite.
Yeah, it's entirely different. Whole dark matter, you can have 1 EV or 100 EV, some kind of this thing. Well, neutrinos that people talk about, but it doesn't seem to be agreeing. So there are problems with cold dark matter, and some of the problems are related to simulations which we do. So we have to take everything with just. Okay. Yes.
Yeah. So the very assumption that the photon placed inside the photon is some mass, doesn't it violate the principle of relative equals gamma square, where we
yeah, well, it doesn't violate it because there is a velocity which is universal velocity.
Yeah,
that will be there. Your photon, if it has a mass, since it is so tiny, like neutrinos, it will travel with velocities which are very close to that. If 3 lakh kilometers is that value, you will find that it is traveling with 2,99,999.99999. How many nines you want to put, you can put it. So the difference will be very, because I'm giving the mass is something like 10 power minus 22 electron volt. It is extremely, it's even worse than neutrinos. Neutrinos, at least people expect 0.5 or 0.2 electron volt kind of this thing. Even that travels only, it comes through the earth and goes to the other side. No problem. So that is the kind of.
Then what does this? Sorry. Then what does this limit correspond to? The universal limit of the.
So there is a fundamental limit which is there as I. So that's where I have to start with some beginning. That there is a fundamental value for the velocity which cannot exceed. That's what special relativity will tell you. That value, in fact, none of the particles will travel with that, including photon. Including photon.
But you mean this is an axiom? That velocity, that they can't exist at any object traveling to that?
Well, I start, only thing is I will work out within this thing when there is a big bang. There is large number of particles are created at the energy scales at a time scale of 10 power minus 15 seconds or something. And that plasma is there. And that plasma, if I apply the same Anderson-Higgs mechanism, it will create its own Higgs. And that Higgs can play the role to make the photon which we play with in our universe right now is having this kind of. That's what I
But what you are simply saying is that this universal velocity, but you are making two statements. One is that we have not identified any particle which travels with this universal velocity. But you are making even a stronger statement that it is in principle.
No, okay, probably that is incorrect. I don't want to make that stronger statement. If it is there, I would be happy. I would be happy. No, for example, if the photon is really massless, but this ultralight kind of candidate, when people have been talking, is helping in dark matter, it can fit in within your framework.
Okay, let's have the last question there.
While motivating, the dark matter mentioned some problems like the transport problem as a missing channel. So, from what I understand, these problems can be resolved by the methods like adding subject or like baryonic feedback, adding baryonic feedback in something. So, is there any other strong motivation for having ultralight candidates?
Well, so it's a question of some of them are simulations, n-body simulation, and we have to, if somebody claims that I can add something and get it, they have to show it. They do that, then people will take observable things which will come from such an addition. Whatever addition you do will have its own problems.
Can I?
Sure.
So one thing you said that yes, the photon in plasma acquires mass. So you ought to have something similar to say that photon overall requires a mass, as a non-zero mass, however small, it ought to have an interaction with something else to give it a mass.
That can be a new complex scalar field which can add. You can add.
You ought to have something additional. So you have some additional field which you can give.
Yeah.
And the second question is your dark matter is a fluid.
Fluid, yes.
But the galaxies or the clusters of galaxies, its equilibrium is the virility, where the only interaction is gravity. There is no other, you can't have a fluid. So that's.
The fuzzy dark matter independent of photons have been reasonably successful because whatever explained by cold dark matter is explained here. So those questions will be answerable within that same.
I see. I think in the same spirit as we take dark matter as also something like pressureless,
Yeah, I think that basically overall, if you see this thing that if it has to have an immediate, then the interaction between the elements should be only gravity. You can't have any other gravity. By putting it as a fluid, you are introducing other interactions.
Okay,
it's not.
So this is the fuzzy dark matter when people don't talk about some scalar field.
Fuzzy is everything fuzzy.
No, it's some kind of axiom like field phi, which is there, and the question is there self-interaction? Phi power 4 with a small value, lambda phi power 4. People have taken that kind of, so it is going beyond the gravitation. That is the kind of self-interaction.
Okay, let's conclude from 10 again to